Good morning, dear students. Okay, ഇന്നലെ നമ്മൾ അനലോഗ് ഇൻ്റഗ്രേറ്റഡ് സർക്യൂട്ട് EC204 മോഡ്യൂൾ 1 ഫസ്റ്റ് പാർട്ട് what is differential amplifier, what are the different configurations, what are the non-ideal characteristics of differential amplifier, what are the different mode of operation, that means differential mode operation and common mode operation. ഇത്രയും കാര്യങ്ങൾ നമ്മൾ പഠിച്ചു. Okay, today നമ്മൾ റിവിഷൻ ചെയ്യുന്നത് ഫസ്റ്റ് മോഡ്യൂളിൻ്റെ ഫസ്റ്റ് പാർട്ടിലെ frequency response of differential amplifier. Okay, already EC205 electronic circuits നമ്മൾ പഠിച്ചിട്ടുണ്ട്. What are the high frequency response of an amplifier? So here for a differential amplifier we have two matched transistors Q1 and Q2. So here we are going to consider a half circuit, a differential mode frequency response of half circuit. Now here some new capacitors. We know C pi and C mu are the high frequency capacitances, and the DC response AD equal to the final output, differential output V suffix OD divided by the differential input V suffix ID, that is the differential mode gain AD. Now AD equal to minus GM into RC of R pi divided by R pi plus RS. It's the expression for the DC responses of a half circuit. Now the frequency response of differential amplifier, we can modify this figure by applying Miller approximation. So we know what is a Miller theory or Miller effect or Miller approximation to find the frequency response. That is, a series capacitance C mu is converted into two capacitance, two parallel capacitances, one belong to input side and another belong to output side. That is called Miller theorem or Miller approximation. So here we have C in, that is the capacitance looking from the input side. The total capacitance C in is equal to C pi plus 1 plus Gm into RC C mu. Now here the resistance seen across C in's terminal, that is the input capacitance terminal, the total resistance RT equal to RS parallel R pi. Here I have given RT is equal to RS parallel R pi. Okay, now here the frequency response of differential amplifier, that is the common mode frequency response. In this figure we analyze the differential mode frequency response. Now here we have the common mode frequency response. This is the equivalent circuit, that is a half circuit. Now here we have the common mode input signal VICM. Then now this is the equivalent diagram. Now here along with C pi and C mu, here we have some other capacitances also, that is the one capacitor, emitter bypass capacitance. Here we are taken CE by 2 because here we are considering only the half circuit. So that is parallel to this emitter resistance REE. So here the DC response of that is the common mode gain AICM is equal to minus GM into RC divided by 1 plus 2 GM into R suffix EE. So this ZE we can define the impedance between the emitter and ground. So ZE equal to 2 REE divided by 1 plus RECE into S. That is the impedance between the emitter and ground. Now here the frequency response of differential amplifiers. Now the common mode gain ACM is equal to, is approximately equal to minus GM into RC divided by 1 plus ZE into GM. For GM into ZE greater than 1, then ACM becomes minus RC into 1 plus SREE into CE divided by, that is 1 plus SRE CE divided by 2RE. This response has 0 at lower frequency. So omega Z is equal to 1 by REE into CE. The frequency response from 0 to omega z. Now here we have different cutoff frequencies. The angular cutoff frequency omega z. We will see in our next slide. We have the frequency response curve. Okay. Now here the frequency response from 0 to omega z will be a straight horizontal line, that is 0 dB slope. You can see here we have up to omega z, here we have a straight line. Okay. Now after omega z the slope becomes plus 20 dB. That is the response of common mode response of a frequency response of a differential amplifier. That is, the common mode gain of the amplifier increases at a rate 20 dB per decade or 6 dB per octave. Now you can see here, this is the second graph showing the common mode response. Now up to omega z, up to omega z, the response is a flat, that is horizontal line with this 0 dB slope. After that the response is increasing, that is the common mode gain is increasing at a rate 20 dB per decade or 6 dB per octave. Now here it is showing 20 dB per decade increasing the common mode gain. Now the second graph B shows the common mode gain. Okay. Now here we have the frequency response of differential amplifier. Next slide. Now here the CMRR frequency response. So what is CMRR? We know what is a CMRR. It is the ratio of AD by AC. That is the differential mode gain by common mode gain. So it is the ratio of frequency response for differential mode gain and common mode gain is plotted. The frequency response of common mode rejection ratio shall be obtained. That is, if the ratio of frequency response of differential mode gain and common mode gain is plotted, the frequency response of common mode rejection ratio shall be obtained. Now here in this CMRR frequency response has 0 dB slope from 0 to omega z, minus 20 dB slope from omega z to omega h, minus 40 dB slope from omega h onwards. Okay, we will see in our third graph, this third plot indicating the CMRR frequency response. Now these are the frequency response curves of differential amplifier. The first one showing the differential gain response or the differential frequency response. Now the next one is the common mode gain or common mode frequency response. Now the third graph plot showing the CMRR frequency response. In that CMRR frequency plot, it is very clear that up to omega z there is a flat response. After that omega z to omega h, here we have 20 dB per decade, that is minus 20 dB per decade variation. Now from more than, that is from omega h onwards, there is a minus 40 dB per decade slope. Okay, these are all about the frequency response of differential amplifier. So these graphs are very important. Okay, now next we see the multi-stage differential amplifiers. In the electronic circuits paper course, we studied different types of multi-stage amplifiers. Multi-stage means more than one stage amplifiers. In order to get high gain, we go for the multi-stage amplifier. Now here the multi-stage differential amplifiers. Why? Normally we know that the advantage of differential amplifier is that it is very sensitive to noises and interference. Not insensitive to common mode input signal, then differential stages are extremely easy to couple directly. Already we studied that two advantage of differential amplifier. Now the differential pair stages can achieve common emitter performance without having to use emitter capacitors, and thus we can again use higher gain CE gain stages. Okay. Now here showing the output of Q, that is in a differential amplifier basic pair, we have the output terminals are the two collector terminals of two transistors Q1 and Q2. Now these outputs are given to the basis of next stage differential amplifier Q2. Then along with differential amplifier multi-stage, we are using here we are using an emitter follower. at the output to reduce the output resistance, and also the above circuit contains two cascaded CE gain stage, a level shifter to achieve a quiescent or output voltage of 0 volt, and an emitter follower at the output reduce the output resistance. Okay, I will share the notes along with this class. Okay, എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിക്കാം. നിങ്ങൾ ഈ ക്ലാസ് നിർബന്ധമായിട്ട് കേൾക്കണം. നിങ്ങളുടെ ക്ലാസ് നോട്ട് തന്നെ റെഫർ ചെയ്താലും മതി. അതിൻ്റെ കൂടെ നിങ്ങൾ ഈ ക്ലാസ് നോട്ടിൽ നമ്മൾ ടച്ച് ചെയ്യാത്ത ടോപ്പിക് ഉണ്ടെങ്കിൽ ഇത് കൂടി നിങ്ങൾ എന്ത് ചെയ്യുക, ഉപയോഗിക്കുക. എന്നിട്ട് നിങ്ങൾ നല്ലവണ്ണം പ്രിപ്പയർ ചെയ്യണം. ഈ റിവിഷൻ കഴിഞ്ഞ ഉടനെ നമ്മൾ നെക്സ്റ്റ് മോഡ്യൂൾ ആരംഭിക്കും. അപ്പോൾ ഇന്ന് തന്നെ ഞാൻ ഒരു ലെക്ചർ കൂടി ഉദ്ദേശിക്കുന്നുണ്ട് നമ്മുടെ ഫസ്റ്റ് മോഡ്യൂളിൽ റിവിഷൻ പൂർത്തിയാണെങ്കിൽ നമുക്ക് 2 ലെക്ചേഴ്സ് കൂടി വേണം. അത് കഴിഞ്ഞാൽ ഫസ്റ്റ് മോഡ്യൂൾ കംപ്ലീറ്റ് ആവും. ഓക്കെ, യു പ്ലീസ് ബി വിത്ത് മീ ടു കംപ്ലീറ്റ് അവർ പോർഷൻസ്. ഓക്കെ, താങ്ക് യു.